Okay. I will talk about information-centric networking, which I suppose you don't have any idea what it is. And its security, privacy, and censorship considerations. Most of this presentation is actually about the first point. What the hell is this information-centric networking? And then I will, of course, also touch the other points, which are quite important. So, what's the current situation in the internet? Cisco predicted that in 2015 we will use 966 exabyte of traffic in the global internet, which is quite a lot. 90% of which from TV, video, and peer-to-peer, stuff like that. Also, mobile data traffic is expected to increase, and what currently is being done is that there are applications which are being put on top of the existing infrastructure in order to cope with this traffic. So we have CDNs, content delivery networks. Maybe some of you know about it. For example, Akamai. Basically, they deliver content on behalf of the content provider by putting caches near the final user, but you have to pay for it, of course, if you want such a service. Peer-to-peer, of course, and so on. This is not the optimal solution. So, what is a possibly better solution? That should be information-centric networking, of course. The idea here is to shift the paradigm from I need something, it's there, I take it from there, to I need something, I need this thing, I ask if somebody has this thing and I try to get it. I don't care what this thing is. So, while on packet shifting, switching or circuit switching networks, you in the end try to communicate directly with somebody who can be on the other side of the planet. Information-centric networking tries to basically give names to things. So you ask for the thing, and you don't care where the thing comes from. So what problems does this information-centric networking thing solve is caching, because in the current internet you don't really have that much caching in general. Caching happens usually on close to one or the other end. So close to the client, for example, there's a corporate network or something, and you have a big cache there, or you have a cache at the remote site to cache the results of the queries. Wikipedia has huge caches. But in the middle of the network, you don't have caches. And you cannot cache content retrieved over SSL. That's the whole point of SSL is to hide what goes through the connection. So nobody can see in it, nobody can cache it. The point is that SSL is being used as a way of securing the objects that are being delivered. That's the wrong approach. We'll see later. Content delivery networks are expensive. Nobody can just come up with and say, okay, I will put my website on a content delivery network like Akamai or something. You can. It's expensive. Moreover, SSL doesn't guarantee that you will actually get the thing you wanted. SSL guarantees that you are talking with the other person, or the other end, and that's really the person you want to talk to. That's really the server you want to talk to. But doesn't say anything about what you are getting from it. So if the server has been compromised, you're getting shit. Multicast just doesn't work in the public internet. And you can forget about delay tolerance. I mean, there's some studies about delay tolerant networking, but nothing there really. So the idea is that, as I said, you ask for an object by name. You don't care where it comes from. But you still need to be able to determine if the content is what you asked for. Because you want something, you don't want anybody to tamper with the content you got. If you are installing a software package, you want to be sure that that's the thing the authors put up, and not something that somebody has tampered with viruses or stuff like that. Also, caching everywhere. Therefore, you will reduce the bandwidth usage over the whole global internet, and improve user experience, which never bad. Incidentally, reaching challenging environments, mobility, delay tolerance. There are quite some places on Earth that don't have a permanent internet connection. What happens presently is that there are ad hoc solutions to provide some form of connectivity to those communities. Or in case of disasters, we saw with the disaster with the earthquake in Fukushima, Japan, and earthquake in Haiti, and so on. When even if you have an infrastructure, then you can always have a disaster that disrupts everything anyway. And in that case, it's not easy to let messages pass by. Even if you just want to say, hey, I'm still alive. It's not easy. And of course, since normally the infrastructure is there in case, for example, of catastrophes, then you just don't have the infrastructure for it. Okay. So basically, we have objects which have names. That's basically all that we have. So we have to put lots of information in these names. Names have a fundamental role in the whole system. We name objects and not hosts. Therefore, objects need to provide some kind of self-certification, self-verificability. For example, you can put the hash of the content in the name, and stuff like that. In the end, is nothing. This information-centric networking thing, in the end, is nothing completely new. It's just putting all the things that are already there together in such a way that it works, hopefully. I mean, Debian packages, they have the hash signed by some kind of public key inside. That's already there, but it's used only for that. You cannot download, I don't know, a web page anywhere and have it signed by the public key of the publisher. You can use SSL, but that has other problems, as we saw. So, there are several possible design choices for an information-centric networking infrastructure. So, okay, what do we want to put in the name? How do we resolve the name? If we want to resolve the name, how do we route? And what kind of networking model? I will explain this point. So yeah, should the names include cryptographic parts? Should the names be human readable? This is important because if names are not human readable, then you need human readable names, and then you need a way to bind the human readable name with the non-human readable name, and then we are in the same situation as before. We need to resolve a name to some other thing which is not a locator, it's not an address, but still we need to resolve it. On the other hand, we can just say, okay, names are not human readable, but then it's hard to just write, for example, a billboard ad with a huge sequence of almost random letters and have people remember it. Should names reflect the topology? There are some information-centric networking approaches in which the names reflect the topology, so how nodes are connected. That has some problems because when nodes move, it just doesn't work, basically. Yeah. And name resolution, well, is it really needed to resolve a name at all? Can't we just send the requests along the path where the object is? But then we need to know where the object is. So there are actually some drafts about possible naming schemes for information-centric networking. This is just an example. So this is an example, and you can see basically it's an SHA 256 hash of the content. That's the thing. It's not really human readable, but it works. So if you ask for this object and you get this object back, you know you can determine immediately if you got the object you asked for or not, because you just checked it. You just check the hash. If it matches, then it's the object you asked for. If it doesn't, then somebody did something wrong or malicious, or well, maybe just some hardware problems, but yeah, right, hardware problems. Yep. So, if you need to resolve the name, then you get back some kind of locator, some kind of address that tells you where to get the object. And then the whole critical point of the network is basically this name resolution process. This is called two-step approach. Because first you resolve the object, the name, and then you fetch it. Or, well, more step approach. I mean, you can always get something else that you still need to resolve, and so on and so on. The one-step approach is more direct. You just ask for the object and you somehow get it back. You don't need to resolve it. This can work with hierarchical names. There are some ICN approaches, some information-centric networking approaches, in which they basically have the topology embedded in the names, so every node knows where to forward the stuff to, because it's within the name. So, oh, I need this object. Where is it? It's far away. Let's send the request that way. Structured flat names means that the topology is not in the name, but the name has some structure. So you can do request aggregation, something like, oh, all the names with this property or with some kind of value inside, with a given property, with a given value, you just say, okay, let's put everything, let's just send everything to that way, for example, or that way. You can do some kind of routing over it. The funniest thing is unstructured flat names, like basically the hash. That's completely flat and unstructured. There's no structure in it in the first part, at least in the first example. There is no way to know where to send a request for that object unless there is some other infrastructure in place. But it's completely possible to do routing over flat names. There are several papers about that, doing routing over flat names, unstructured flat names. So it's possible, but it's not exactly the easiest thing to do. So okay, if you want to resolve the name first and then fetch the object somehow, you need to resolve this name, and okay, you can do DNS style or DHT style. That means a distributed hash table style. That's basically the same concept behind many peer-to-peer networks, like BitTorrent, I think, even uses a distributed hash table. On the other hand, you can route on names, which it's quite tricky, because if you have several trillion objects in the world, you cannot build a routing table with 1 trillion entries inside. It gets really tricky. Oh yeah, something I forgot. This one-step, two-step approach, actually, you can also do both at the same time. I mean, you need to decide, oh, my information-centric networking approach will use one-step or two-step, or you can also decide that you don't care, you can use both. Which is question?
How would this work? How would this DNS aspect work? So would it be a central server that has all the addresses, or would it be a kind of peer-to-peer routing process?
Yeah, that's the whole point of the thing. DNS style means basically, yes, using some kind of tree-like infrastructure. So like the DNS. So you ask your local DNS about any address. If it knows about it, it will reply. Otherwise, it will forward it up to the tree, and then you will reach some kind of route, and then you will descend down again until you find the server that has the address you need. That's basically how DNS works. So I don't say here that we want to use DNS. You can use DNS as it is. You can just put some extra values in some extra fields and use them to do information-centric networking. There are some approaches that do that. But yeah, I mean, you easily have a central point of failure this way. I mean, or yeah, I mean, you can have fault tolerance on the near the root of the tree, but I mean, especially if you are cut out of the network, it doesn't work, because you can have some kind of replacement or backup strategy for the root of the tree if something happens to it. But if you are out of the network because there has been a catastrophe or something like that, or well, let's be less catastrophic, you're just in a place where you don't have good connectivity, it just doesn't work. Then again, yeah, so basically this thing about one step, two step, you can use both. Basically, you send a request and you can get an object back, but you can also get some kind of redirect. So you don't even know when you request an object what you're going to get back, if the object itself or a redirect maybe. And this approach works, more or less. Yeah, push-based or pull-based. What does it mean? Push-based means you have made something, you want to publish it. You push it into the network. You publish it, you push it to some, you send it to some other node which will do something like storing it or sending it to a further other node for storing it. Pull-based means, okay, you publish the object. It means that if somebody requests the object, then you will serve it. This means that you need somehow to advertise to the whole world that you now have that object, which is not exactly the easiest thing to do. Of course, if you're using hierarchical names, it's slightly easier because then your object will have some hierarchy behind it. So then it can work. You only need to put this address somewhere where people can click on it, and the routing will just work. But it's not the best thing. Also, for example, what if you want to start a connection because you want to start an interaction with somebody? This is an approach being developed in the United States. It's called CCN, content-centric networking. Basically, their solution is that you request something, and basically you request the other party to send you a request. For example, if you want to do a phone call, you need a bidirectional stream. So basically, you create some kind of ID for the connection, and then you request the other party to send you a request over that ID. It's, I mean, they did it. It works, but it's not the best thing, I think. Okay, so this is basically what this information-centric networking is. It's as I said, it's nothing really new. It's just taking everything that is there and putting it together. So, caching, self-certifiability or verifiability of names, of objects actually, and stuff like that. But what it means when you put everything together, what happens then when everything is there and hopefully actually working? So man in the middle, it's really more difficult to perform because the network by design allows anybody to deliver any content. So you don't have to worry, because if somebody mangles your data, you will see it because the hash will not match. What could happen is that people could, for example, publish fake objects. I put up fake object, so you request the object, and the caches will give you the wrong object, but then you will discard it because it's fake. This means that you will never get to use the fake object, but you will also never get the right object unless you manage to convince the cache that they have to drop the fake object. This means, for example, that caches will have to start to verify the objects. So the ability to verify that the content you required is the actual content that you get is usually performed by the requester. Caches on the path don't need to do this verification step. This means that caches don't have to do too much work. But if too many fake objects start flying around, then caches basically will stop to work at all, because they will be filled with fake objects, or they will be forced to start verifying the objects. So doing a lot of work, because then you have to check everything that comes by. Yeah, and of course, if you are, instead of using a hash in the name, I mean the hash of the object in the name, you can put a public key or the hash of the public key in the name, and then use that to verify that the content is signed with that key. And then you have key distribution problems. Okay, the problem is still there. Privacy consideration. This is really funny, because here, since objects can be served by anybody in the whole network, the requester, the request will not necessarily reach the publisher. So the publisher will never know how many people and who got what from where. This also means that you it's harder to do this country-based censorship, because you cannot say, okay, it's coming from this country, I block it. You don't know. I mean, you cannot do it on the central, on the publisher side, because you cannot know where the request comes from. What can you possibly do is then to start filtering on the border, to put maybe some flags inside the objects, so that nodes on the board or on a country border will refuse to send the object back. But then that starts to be a lot of work, because instead of just putting a simple check at the publisher side, which is trivial, I mean, anybody could do it, then it starts to be really, really tricky to do it. Of course, access nodes see all the traffic, so if you have some kind of dial-up connection and stuff like that, of course, the first router will see all your requests and all the replies to that request, of course. Okay. Yeah, that's actually a little worse than the current situation, because, I mean, yeah, now everything passes through the router as well, but, I mean, it's just IP or TCP connections going on. You don't really, I mean, unless you're using deep packet inspection or stuff like that, you don't really see what's passing inside. Of course, deep packet inspection is now commonplace, but in general, this approach makes it worse. Okay, because that's part of how it works. Of course, you can always use end-to-end encryption, but yeah. So this thing about caching everything everywhere is nice when you need to get content. It starts to be less nice when you, for example, are doing a phone call or something like that, and then your phone call, for some reason, is cached. And all over the network, you have pieces of your phone call. Of course, you had encrypted it, okay, but still, it's there. If somebody after, say, 1 day or 1 week wants to try to decrypt that conversation, it's now possible to attempt some kind of attack on it. Normally, you would need to intercept the live conversation. Here, if for some reason the phone call, for example, is cached, then it's there. Wow. So this is something that needs to be taken care of. Of course, you can put some kind of flags in the requests and objects that say basically, do not cache this, please. But then you have to try to trust the caches not to cache that, and yeah, trust the government, right? What could possibly go wrong? It's actually possible to implement a censorship avoiding mechanism with plausible deniability. Basically, the approach works that you ask for several different chunks of objects, and you get back. I'm oversimplifying it, but basically, you get back the several chunks together, and in such a way that basically you cannot, nobody can prove or disprove that you wanted some piece of content instead of another piece of content. Yeah. So, you want to close down a website? Well, you can't, because I mean you can shut down the publisher, but if the objects are all over the network, because it was something interesting, something interesting that maybe the government of some country wants to shut down for some reason. Yeah, you can't. Okay, you can just shut down the single page, and you have basically to take control over the whole network and force every single cache to part the content, which is not that easy. Yeah, or filter directly at the access node. Okay. But then again, this information-centric networking thing, it works even. I mean, it's not a centralized structure. It's not thought to be. So it works even if you are disconnected, or if you are in some kind of disconnected graph of the whole network. So if for some reason the government decides to shut down the whole internet, let's say, the thing will still work. I mean, there are several countries in which you don't have internet access, or not. You have only very restricted access. Well, you can just say, okay, screw it. I will just send messages to my neighbors, and they will send there to their neighbors, some kind of mesh networking. It will just work. And the point is that also, since content is distributed and copied in the caches as part of normal operations, basically copyright trolls will not have an easy time to shut down things. You cannot say, oh, your cache contains a copy of my copyrighted work. Yeah, that's part of how it works. So if they put up some kind of copyrighted, their precious copyrighted material online, and then they want to take it down, and then not all of it is taken down because it's still cached somewhere because it's something that was requested. They cannot basically take action against these caches because it's just part of the normal operations of the network. Something interesting. Okay. So basically, this thing is still quite open research topic. There's lots of projects on this topic, and yeah, because it solves many problems, like I said before, and creates new ones. And if IPv6 needed 15 years and is still not there, imagine something like this, which could really could be really beneficial to the world. As the last thing, if you want to play with it, this is a project I'm working in. We have some cool open source code you can start to play with if you want. Questions?
Just can you go back for a few moments to the last slide so we can copy the URL?
Oh, sorry.
In the current model, the incentive for the host to host files is because nobody is going to do it, right? If I have a website and I want to keep it up, I'm paying myself for the server because nobody's taking care of it, and that creates a weakness. So that if somebody wants to shut me down, you just cut my server or just cut me out. The redundancy that you describe is in the fact that it's cached everywhere. So the content would be cached along across the internet in many different places. But what would be the incentive for the node owners to cache content from other people?
Yeah, well, that's basically the same thing as what's the incentive of router owners to route your traffic? So, yeah,
What do you mean by that? What kind of router?
I mean, if you ask for an object somewhere on the net, then you establish a connection, and your connection will go through many routers on the path, and they will forward the message for you, right?
Yeah, sure.
Why?
Because there's a whole chain of payments down the line.
Yeah, okay. So you can do the same thing as for information security networking, basically. It's not that much different. Moreover, the cache owner actually has a benefit, because if I receive a request for an object, and then I have to forward it, for example, to another autonomous system, then unless I have some kind of agreement, I have to pay for this for that bandwidth, and then the requests come back. Let's say that the object is popular. You want to cache it, because then you will serve it from the cache instead of going every time over the other autonomous system.
Okay, so
you save money.
So the incentive is for the people who are doing the routing currently to host the system, not for the people who are currently doing the hosting, right?
Yep. Yeah, but I mean, if this, this thing will make many people unhappy. Basically, if you know how a content delivery network works, like Akamai or stuff like that, this will basically put Akamai out of business.
Is there any live project that we can look at?
Yeah, that one?
Yeah, but how large is the scale where you implemented an ICN? And what are your experiences with it?
Okay, this is quite a broad question.
For example, is there a university network that you put up in the lab to as a proof of concept that is quite large?
So there are several projects. In most cases, you can just download the sources and set it up yourself if you want to try it. There is no, so to say, backbone. Also, there is no centralized ICN thing. It's not like IP. IP is a protocol. ICN is more like an idea. I mean, ICN is like to say packet switching networking. It's a way to do stuff. There are some implementation of this idea. One is that one. Another one is CCN, for example. Now it's called NDN, I think, because they realized that the system doesn't work well. Yeah, but there's no kind of backbone or experimental backbone. Okay, so mostly there are some experimental nodes from the project partners. Yeah, nothing really open at the moment so far, but I mean, nothing stops you from getting the sources and try to do it yourself, basically.
Well, maybe just coming back to your remark, there are actually two thoughts I'm having in the back of my mind, which are not like fixed or implemented, but which could show the direction. One thing you could do if you have a cache, you could have something like requiring the cache to hold a copy of the file. And if you're using a hash function which allows some zero knowledge type of proof, I could ask you to prove to me that you're actually having the file, not only by acknowledging I have a file which has the hash. So that would be one part in the mosaic, and the second part in the mosaic could be by communication. I communicate with you, so I do some routing for him. At the same time, by intermingling certain bits, I do so because I get a benefit from 20% of the traffic. So I have some motivation here. but I don't see like completely how these individual parts fit together to a mosaic. But that could be like two building blocks for giving an idea for. You could combine it with some Bitcoin blockchain, which kind of keeps track of that and like counts whether you're a trusted person, and if you go beyond a certain measure, you lose your ability to contribute. So I think there are a few building blocks in here. But the good question, of course, is there a working system which is like solving all these problems at the same time?
Also, one point that interests me is where do I get the hash list? For an example, if I want simple online banking, and well, that's quite sensitive, and if we have, for example, only this package-oriented kind of delivery, and it's not important where I get the packets from, but I need to have packets signed by my banking company.
Yes, and probably also encrypted, because maybe you don't want your personal data to go around the net. Yes.
Yeah, but how I know which packets I should have to do this online banking?
Yeah. Okay. So the problem is to get to know the names of the objects you want. Well, the whole thing is most URLs today are not human readable anyway, because they start with some kind of address and then slash and then some stuff, which usually is a long sequence of letters and numbers. I'm sure that if you go on your online banking site and you try to do anything, you will see that the URL that you request every time is just a long sequence of apparently garbage of random characters. Maybe some are really random. Maybe some have some meaning you don't know. So basically, the point is, how did you get there? You clicked on a link.
So we still use the IP format and DNS to look up my list, for example.
You need some way to know what you want, but I mean, search engines are there for this. You go on Google, you Google something, and you get some results, right?
But what if I need like a session, unique packets?
Yeah. Okay. You can still do it. I mean, the way of putting the hash of the content in the name is one way to do it, but you can, as I said before, you can actually put the public key of the publisher in the name, and then use that to verify the content, because inside the content itself you have the hash signed with the public key, so you know it's that one. And at that point, you can just start sending requests for that object. I mean, for an object with the name that contains basically the request you want to do, followed by the hash of the public key, and then just verify that it matches. It's basically doing SSL by hand, more or less.
I was a bit worried by the process by which you find the name, or the process by which you identify your website. In this name resolution thing, human readable address for a hash.
Yeah.
Unless you're based on a central authority like Google or something, constantly it's centered. There's no way for somebody to know that the link they're clicking on
Yes.
is really
Yes.
is really the
Yes,
book that
but
they-
I mean, SSL works exactly in the same way. If you click a link and it's over SSL, and then you get a certificate, there is a central authority that, and we saw how bad it works actually. So, yeah. Okay, no more questions?